Hello everyone, this video explains the use of 2D rigid body. The rigid body is a scientific abstract concept used in mechanics to reflect the characteristics of an object, as well as an ideal state of mechanical expression model. It refers to an object whose shape and size do not change, whether in motion or at rest. In reality, such an ideal model does not exist. If the changes in the object itself do not affect the entire motion process. To simplify the research problem, the object is still treated as a rigid body. In the LayaAir engine, the 2D rigid body component class is LayaAir rigid body. Next, we will explain the use of rigid bodies in the LayaAir IDE. First, it is necessary to select the appropriate engine module in the Project Settings panel. Then, click on a 2D node in the Hierarchy panel and add a rigid body component in its Property Settings panel. After adding the rigid body component, let's take a detailed look at its parameter settings. The first parameter is type. Rigid body types are divided into static rigid body, dynamic rigid body, and kinematic rigid body. The default is a dynamic rigid body. Static rigid body is typically used to represent immovable objects, such as the ground, walls, etc. The mass and inertia of static rigid body is infinitely large. Therefore, it is not affected by external forces, nor do it exert force on other rigid bodies. The characteristics of the static rigid body are: it always remain motionless. No matter what forces are received, it will not move, it is not affected by gravity, and velocity is zero and cannot be set. Dynamic rigid body is the most common type of rigid body, used to represent objects that can move and are affected by external forces, such as characters, spheres, etc. Dynamic rigid body has mass and inertia and will move according to external forces. The characteristics of the dynamic rigid body are: it moves according to the forces received, it is affected by gravity, and velocity can be set. Kinematic rigid body is a type that falls between static and dynamic. It is not affected by external forces, but can move by setting linear and angular velocities, rather than being directly acted upon by external forces. Kinematic rigid body is typically used to control joints, platforms, etc. The characteristics of kinematic rigid body are: it does not move according to the forces received, it is not affected by gravity, and velocity can be set. The main difference between kinematic and static rigid body is that kinematic rigid body are usually made to move by setting linear and angular velocities. The second parameter is the gravity scale factor. First, in the Project Settings panel, under the Physics 2D, the gravity acceleration is used for global parameter settings. This setting supports gravity settings in both x and y directions, with the default being the gravity acceleration value of 9.8, in the positive y-axis direction vertically downward. The larger the value of gravity acceleration, the faster the objects affected by gravity will fall. Meanwhile, the gravity scale factor on the rigid body component is used to independently affect the gravity effect on a single dynamic rigid body. A value of 0 indicates no gravity. Values greater than 1 indicate multiples of normal gravity. The larger the value, the greater the gravity. Negative values indicate gravity in the opposite direction. The smaller the value, the greater the opposite direction's gravity. It's important that in order for rigid body to be affected by gravity, a collider physics component must be added. Here adding a box collider Next, 3 sprites are used for comparison, setting their gravity scale factors to 1, 0.5, 10, and -1, running it to see the effects. The following 2 parameters are angular velocity and angular damping. Angular velocity refers to the speed of an object's rotation around its center of mass. It is a physical quantity that represents angular displacement per unit of time, with the standard international unit being radians per second. Starting from LayaAir 3.1, to make it easier for users to understand and set intuitively, this can be directly set as the degree value. When the angular velocity attribute is set to a positive value, it will rotate clockwise. When the angular velocity attribute is set to a negative value, it will rotate counterclockwise. The larger the absolute value of the attribute, the faster the rotation speed. The default value of the angular velocity attribute is 0, in which case it will not rotate. We compare 2 sprites by setting their angular velocities to 1 and -1, and observe the effect upon running. In the real world, rotating objects typically decelerate over time due to external resistance. Angular damping is precisely the parameter used to simulate the gradual deceleration of a rigid body during rotational motion. Specifically, the angular damping of a rigid body is a rotational damping coefficient relative to angular velocity. This means that angular damping will cause the rotational speed of the rigid body to gradually decrease. By adjusting this value, one can control the degree of deceleration during the rigid body's rotation. The default value is 0, indicating no damping. We compare 2 sprites by setting their angular velocity to 10, and the angular damping to 0 and 1. Run to see the effect. Next are linear velocity and linear damping. Linear velocity, also known simply as velocity, refers to the speed at which a rigid body moves along a straight path, without considering its rotation. Starting from version 3.1, these 2 components are measured in pixels. Moreover, this vector value is also a vector quantity, including both magnitude and direction. The default value of linear velocity is 0, indicating that there will be no linear motion in the absence of force. X represents the linear velocity component of the rigid body, along the x-axis horizontal direction. Y represents the linear velocity component of the rigid body, along the y-axis vertical direction. We use 5 sprites to demonstrate different states of linear velocity. Run to see the effect. During motion, a rigid body may experience a damping force in addition to external forces, which is proportional to its velocity. This damping force is known as linear damping force. Developers can adjust the intensity of the linear damping force experienced by the rigid body during its motion by setting the rigid body's linear damping attribute. The range is from 0 to infinity. The default value is 0, indicating no damping. We compare the effects of with and without damping using 2 sprites. Both are set with a linear velocity of 200 in the vertical direction, and linear damping is set to 0 and 1. Run to see the effect. Next, let's discuss bullet properties. When an object moves at an extremely high speed, traditional collision detection might fail to accurately capture the occurrence of a collision. This can lead to issues such as tunneling. The reason for this is because Between two time steps of collision detection, the object may have moved a significant distance and left the detection range. This necessitates the activation of the bullet property. It's important to note that, on the physics engine, enabling the bullet property will increase the computational load. Therefore, it is recommended to enable this property only for rigid bodies moving at high speeds. To demonstrate the effect of the bullet property, let's use two sprites. Their horizontal linear velocity is set to -100,000, heading towards a red wall. At high speeds, when the bullet property is not enabled, the collision is not detected within a short period, leading to the absence of a physical collision, and the objects passing straight through to the other side. The concept of an allow sleep property is fairly straightforward. When allow sleep is enabled, the physics engine will put the rigid body into a sleep state if it hasn't moved or been subjected to any forces for a while. Allowing a rigid body to sleep can reduce unnecessary calculations and improve performance. However, transitioning from sleep back to active calculations could result in a delay in response. The decision to enable sleep depends on the specific requirements and a trade-off with performance. In most cases, enabling sleep is a reasonable choice. In addition to the sleep property in a rigid body component, there is also a global switch for the rigid body functionality. In the project settings panel, if the global rigid body sleep functionality switch is enabled, individual rigid bodies can only be set to allow sleep. It's recommended to keep the global setting enabled by default. The allow rotation property is also relatively easy to understand. Allowing rotation in a rigid body means that, when a force or an impact is applied to it, it will rotate naturally according to physical laws. This rotation can provide a more realistic physical interaction effect. Disabling the default allow rotation option will forcibly keep the rigid body from rotating throughout the physical simulation process. In scenarios where performance demands are high, especially when dealing with a large number of objects, disabling unnecessary object rotations can help improve the efficiency of the physics simulation. This is an example where two squares collide, one with the allow rotation option unchecked, and the other with it enabled. Due to time constraints, please refer to the next video for more exciting content.